Welcome to today's SCA webinar with Dr. Dennis Dria, speaking on getting it right with fiber optics, from monitoring frac growth to managing well integrity. Before I introduce Dennis, I'd like to remind the audience that you are muted, but you may ask questions during the presentation using the Go to Webinar question feature. We'll cover the Q&A at the end of the presentation. I'd like to share my slides. Let's see. So today's presentation is getting it right with fiber optics, from monitoring frac growth to managing well integrity. And Dr. Dennis Dria has over 40 years of experience in the upstream oil and gas industry, including 9 years with Standard Oil and 21 years with Shell, with a combination of working in various upstream and downstream segments, including R&D and exploration production operating divisions. When he left Shell in 2010, he was a staff research engineer working in the area of fiber optic technology development. And he's continued to work in that area with fiber optic data management, integration, and technology implementation for well and reservoir monitoring. He's also served as engineering advisor for Shell's global implementation team for reservoir surveillance technologies. And he's been involved in Shell's top 70 global development projects that resulted in field surveillance plans for more than 20 major E&P projects. It was Shell's global subject matter expert on production logging, permanent sensing, and also the subject matter expert for mud logging. He's also experienced in formation evaluation, well logging, and a variety of different aspects of those. Dr. Dria has a BS in physics and mathematics from Ashland University and a PhD in petroleum engineering from the University of Texas at Austin. So the class that Dr. Dria teaches November 4th and 5th is in well fiber optic sensing. That's offered in SCA's training center in Houston, Texas. This is a 2-day training course, and you can see the learning outcomes as listed here. Look forward to more free live webinars that are coming up from SCA. We have Dr. John Rosine speaking on deep water in 2024, science, technology, and valuation. That's on September 12th. And there are 2 webinars in October and November presented by Ellen Cooper-Smith and Ray Spence. The first one is on decision framing for project management, building out quality field development plans. And the November webinar is on the value of information min kit, justifying the information and the tie to future decisions it impacts. We have several in-person courses that are coming up in SCA's Training Center in Houston. August 13th and 14th is Introduction to Subsurface Machine Learning with Dr. Sid Misra. September 30th through 4th in Midland, and October 7th through 11th in Houston, we're offering 2 options for locations for applied subsurface geological mapping. That's a 5-day course. And October 23rd through 25th in Houston, Texas is Alan Cherry delivering the Mapping Seismic Data Workshop. And our upcoming live online courses include Larry Lake and Jerry Jensen speaking on managing mature oil fields with capacitance resistance modeling. And of course, SCA's classes can be taught in your own office as a private course. So please see us to schedule those at the best time for your employees. You can attend the public courses that we offer in Houston and other locations around the world. And some of our courses are also offered live online. And so let us know if we can schedule those at your convenience, or if you'd like to attend one of the public live online classes. In addition to training, SCA offers consulting services and recruitment and executive recruitment. So please let us know if there's something we can do for you. And I'm going to pass the presentation rights to Dr. Dria, and we can start the presentation.
So can you see my screen?
Not yet.
Okay.
May take a minute to load. Now we see it.
Okay, great. All right. Well, thanks everyone for joining me, joining us with this this webinar. And my topic about what are you missing about your well and reservoir is something that we often ask. We want to get the most out of it, and what I would like to do is to start with an example of, it actually is a very nice demonstration of not understanding how your well is working. In a look back survey for Eagleford wells, one service company found that 10 out of 14 stages showed interstage communications. And also that when they did pump diverter to try to help control the injection into the perf clusters, the diverter response was fairly inconsistent. These results were obtained actually by fiber optic monitoring. With that in mind, they did a multi-basin look back and found that in all of the, I think 5 or 6 basins of unconventional drilling and production in North America, that they found communication in 40% of their frac stages. And on average, where they had these problems, they had 40 to 45% of their pumped volume leaked per stage. That is a lot of lost fluid and proppant. That is a lot of lost horsepower that has been, that affects the not just the outcome, but also the capital that you put into stimulating these wells. They found that when they increased to more than 3 or 4 perf clusters, they had non-uniform fluid distribution. The studies that are reported here in these references that I've shown, we come back to answer, we'll get many responses, but well, we pump plenty of water and sand. If we just pump more, we should be able to get our well stimulated, get our fractures going. But I will counter with that with saying, if you always do what you've always done, you always get what you always got. A quote attributed to Henry Ford when looking for ways to improve his operations. We'll end up showing a little bit of value, a few examples where there have been value that has been realized by actually trying to understand what your processes are doing, how are you actually accomplishing what you set out to accomplish. In learnings that have been applied to new wells, meaning the learnings from the monitoring during these fracking operations, is that in the Eagleford, they found a 121% increase in EUR and a significantly lower the decline rate. In 2 wells in particular, they increased the average in EUR increase in 2 wells that were producing 1,000 barrels a day. In the Haynesville, they found a 200% performance improvement in refrac wells which corresponded to more than a 2 BCF increase in incremental production. The estimated ultimate recovery uplift from refracs were estimated using the redesign, and this is the value they get from monitoring just a few wells, an increase in of 30% in the Bakken, 73% in the Barnett, 107% increase in the Eagle Ford, and very substantial increases in the Marcellus and Haynesville as well. So using monitoring data to redesign frac. So not just value in the wells that you're monitoring, but taking that information, moving it forward to use it in future wells. The reported results from several major and independent operating companies show that they had significant value in understanding and optimizing individual well performance. The greatest value was in learnings that they were able to apply in new wells and in often cases new fields, where they were able to use the information they got to calibrate their models, and then use their models to specifically their updated models to more efficiently complete, to place and to complete these their new wells in these fields. They're able to optimize the hydraulic fracture simulation efficiency, reduce cost, and stimulate more stages using basically the same operating costs. They increased the reservoir understanding, and that was able to lead to greater ultimate recovery. So these, I've showed a few references here. The translating it, and it's somewhat difficult to get information from specific operators released, but one example that we have is from ConocoPhillips and their instrumented wells. They used distributed temperature sensing, distributed acoustic sensing, and pressure and temperature gauges. So the DTS and DAS are fiber optic monitoring techniques. They combine that with microseismic, and were able to get a better understanding of the physics from the production from their reservoir, and use that information to calibrate the models with the data and learnings. They apply these learnings that were obtained from just a few of the wells to design the future wells, and they focused on their completion redesign and the well spacing. They found that they were able to increase their resource base by 39%. So what they originally had, applying these technologies and using them to better understand how the wells were operating and to calibrate their models so that they were able to better use them in future developments to increase their resources to the point of globally a 700 million barrel increase shown here. And this is the reference that was published by the ConocoPhillips folks. In the Eagle Ford, BP Lewis Energy operating these wells, they used fiber optic information from DTS and DAS, and there were complementary surveillance technologies that they used, including tracers and production logs and microseismic, but integrating all together with a very significant component from the fiber optics, they were able to get direct measurement of completion efficiencies with the fiber optics, use that with other techniques, other information they got from 3D fracture and reservoir model calibrations, and focused on the cluster efficiency, the stimulated rock volume, and were able to realize enhanced production. The field results showed a 15% uplift for the average type curves using the optimized completion design based on these diagnostic monitoring pilots. What they have shown is the type curve from their baseline well in the blue here, and this uplift. So not only an increase in the average barrels of oil per day, not the average, but the instantaneous production in terms of barrels of oil per day in the red line, and then the both in the data and then in the fit decline curve, but the total an increase in the total volume uplift. An example from a deep water offshore, an offshore reservoir in the North Sea. In the Norwegian sector of North Sea, there was a WAG injection of CO2 and water alternating gas injection. And they installed, and the injection was into multiple zones, and they installed optical pressure temperature gauges and optical flow meters so that they could understand if they were properly controlling the injection of water into these three zones. The reservoir management goals that they realized were that they were able to get real-time pressure, temperature, and zonal injection rates. So this was without any interventions. They were able to look for cross flow in the zonal injections and confirm that they had zonal isolation. The value that they realized is that on this platform, they were able to save 1 to 2 well slots, which since they were able to do that by optimizing their injection, that allowed for additional producing wells to be drilled. From just one injection, and at the time that this was done, back in, I think, 2013 or so, is when those were actually done. The well cost was about 10 million each, incremental with the infrastructure they had in place. They would eliminate one injector, but also the frequent wireline logging. And by being able to replace the wireline is a very significant savings in cost. So how is this done? There are three basic techniques used, or three basic types of sensors that we look at in fiber optics. One is where there is a single point sensor, and the fiber itself is basically used as a communication line. There is an optical sensing element, and this is one which has absolutely no electronics. It's very small, very low mass, so it's going to be resistant to damage from vibration. Don't have to worry about solders and things like that, other effects of temperature. So a light pulse is transmitted down the fiber from a surface instrument. It basically interrogates this optical element, this optical transducer, and then that information is returned through the fiber to the surface instrument unit. It's possible to, with many types of these sensors, to multiplex 8 or 16 of these on a single fiber. It's very valuable and very precise. An example of this is going to be a pressure temperature gauge that basically can replace the a high precision quartz gauge for things such as pressure transient, or lower accuracy gauges that would be used for monitoring sweep or things like that. On the other end of the sensing spectrum, we have distributing sensing, where the fiber is the sensor itself. So this relies on very small imperfections or variations in the glass that are intrinsically a result of the fiber manufacturing process. And you get information from basically every single point along the length of the fiber. The multi-points, there is a multi-point, or what I like to describe as quasi-distributed sensors, which go way beyond the multiplexing that you can do with a single fiber. And these are ones in which the sensing points are basically within the fiber, but they are placed in the fiber when the fiber is drawn or shortly after it is drawn before it is put into a downhole cable. And you can end up putting thousands of these in spacings as small as a centimeter or two apart. So there are instances where strain measuring fibers are implemented in the well, and these have basically in a joint a length equivalent to a joint of casing or production tubing or sand screen. You can have several thousand of these sensors in there, which allows you to get very detailed information, enough to do a specific type of imaging. There's a variety of measurands that can be obtained using these optical sensing. And for the single point sensing, very popular ones are pressure and temperature and flow, some single point strain. There are also single point 3D seismic sensors that are completely electronics free with based on optical sensors. The quasi distributed, we have temperature and pressure, very big items. Very important measurements are made using strain. The strain that is can be done on the downhole tubulars, on the casing, but also can be made on for long term on reservoir strain. So we're looking at events that will cause compaction or dilation of reservoir layers that can lead to either well integrity or subsidence issues. There are distributed sensing. The very first one that was introduced was distributed temperature sensing. There is something called a temperature gradient, which is based on a Rayleigh backscatter. So this is a gradient not in space, but a time gradient. But you can look at temperature changes, very fast temperature changes that occur in locations, and these gradients can be measured in terms of millidegrees, a thousandth of a degree per second resolution. A very widely used technology in the distributed sensing world is a Rayleigh backscatter technique, which delivers a distributed acoustic sensing. And this will be used for acoustic information for things such as leaks, but also for seismic. And then there are strain measurements that can be made. They can be made a variety of methods. Very popularly, we'll get a low frequency DAS or a Rayleigh frequency shift a distributed strain measurement. And these have been used very widely in a lot of applications. So these measurements here that we show, the DTS, the DTGS, DAS, and DSS, distributed strain sensing, all fall in the category you will hear people talk about as being DFOS, or distributed fiber optic sensing. So again, these sensors are all made using the entire length of an optical fiber. One that I have listed, or two that I have listed here that I've kind of got it italicized because they're not really available for commercial, but a lot of development work is going into it, and that is for distributed pressure sensing. So you can get a continuous pressure reading basically along the length of a fiber or a fiber cable. And distributed chemical sensing. There's been quite a bit of work gone into that and some very interesting results. But again, as with the distributed pressure sensing, there is nothing that is commercially available that we can apply at this point in time. Now, how do you make these measurements? Basically, it involves having to get a fiber or a fiber containing a cable with the fiber into a well, and these cables on the outside are going to look very much like an encapsulated electrical cable that you might use for a downhole, traditional downhole pressure gauge. But and they are placed in approximately a 1/4-inch OD stainless steel tube, corrosion resistant tube. So we have this cartoon of a well, the schematic of a well, if you will. So we've got casing that's cemented, and we've got production or injection tubing in the well. We've got a packer. The perforations will be down, or the inflow will be down near the bottom of the tubing. So the tubing will end, and we'll get ability to get flow up the tubing or down tubing into the formation. And in this case, we have an optical cable that is clamped onto the tubing. There are the DMCs, our dry mate connectors, and these allow the cable or the fiber to basically pass through a pressure isolation point, which is in this case a packer. We have another feed through at the wellhead, and a wellhead outlet that is specifically designed to isolate pressure from the inside of the well through the cable, optical cable, and then a surface cable carrying the light to the surface instrument. So the path that is followed is that an interrogation signal will go down this line, down through the well, and will then come back with information and come back to the surface instrument where the pulse, the light pulse is analyzed, and the resulting distributed temperature sensing or distributed acoustic sensing information, for example, will be deconvolved from the signal. There are also options to cement the cable on or apply the cable to the outside of the casing as it is being run in, and then cement it in place. These are both examples of a permanent cable installation, again, where the optical cable clamped to the tubing, and the case where you have the cable that is clamped on the outside of the casing as it is run in and cemented in place. There are also ways to apply effectively a temporary installation, if you will, by doing an intervention. So very much like you might be doing a wire line or a coiled tubing intervention into a well. And the fiber can be actually conveyed on the inside of coiled tubing. So there are quite a few service companies that are offering an instrumented coiled tubing. It can be done during an intervention. So it's quite possible to actually do coiled tubing work, a workover using a coiled tubing, instrumented coiled tubing. And while you're in there, you can get additional information using the fiber optics. And I'll show some examples of those in later slides. There are fiber optic instrumented wire lines, also slick lines, and then a relatively new commercial product is actually a disposable fiber, in which the fiber is deployed into the well, bare fiber, and then it is left in place. Data can be acquired from anywhere from a few hours to a few weeks, and then you basically take your equipment away from the wellhead, and the fiber is just left to it's basically like a strand of hair that is left in the well. There is nothing to pull out. These tend to be relatively low cost installations, or interventions, but they have been shown to give some very, very good results. The company that had come out with this design was called WellSense, and their product is the FLI, the fluid. It's a fiber line intervention, and in North America, Halliburton runs this as the Express Fiber product. With the installation of optical fibers, either in a permanent or as an intervention, we are able to provide basically life of well type of monitoring and information flow. So this notion of having one fiber or one fiber cable, one fiber, multiple applications over the lifetime of the well. So as you've got a variety of different data streams or information streams that you can obtain depending on where you are in the well. You can use it during the construction and completion of the well. This is very very commonly done in the unconventional oil and gas world, where the fracture stimulation stage is monitored very closely using fiber optics, and you can identify such things as operational issues, doing fracture profile, and look for cross-well communications. The notion of when you have, starting at this point in time during the completion through the production stage, through the lifetime of the well, if you have a permanent installation, you're able to do things like microseismic monitoring and to do vertical seismic profiling, again, through the lifetime of the well, to get information about sweep if you're doing an injection, for microseismic monitoring, using that for such things as in injection scenarios, looking at injection out of zone and things such as that. During the production stage, you can use the fiber to do flow profiling. And also during this production stage of the wells, if you have either producers or injectors, you can, in which you have things such as ICDs, inflow control devices, you can monitor those and control those in real time or near real time based on such things as DTS and DAS monitoring across them. All through the lifetime of the well, and this can be up through and including an abandonment, is the application of fiber optics for wellbore integrity monitoring. Excuse me. From the very early stages, you can, if you have it in place and the instruments in place while you are doing the cementing job, you can do a cementing assessment. You can watch the it's very easy to use these technologies to identify the top of cement. During the during the completion, particularly if you're doing something like a fracture stimulation, you can look for casing leaks, and that capability will last you through the lifetime of the well. There also are you have the ability to monitor casing deformation and casing elongation or crumpling, and also near wellbore compaction events and dilation events. So these are all fitting into the notion of being able to monitor subsidence or caprock integrity. So a lifetime, a single installation, and a lifetime of monitoring. These notions also or advantages for the permanent monitoring become important in the CCUS, the carbon capture projects that are starting to be being placed and monitored closely for leakage, as well as for reservoir management of the CCUS process. For hydraulic fracture stimulation optimization, DTS and DAS have been used with other monitoring data to calibrate or constrain models. I show here a panel, a log panel from a publication from Gustavo Ogueto and colleagues, in which they show the results of monitoring from a single stage, and we've got the stages. The perforation clusters are shown here, and these are the stimulated stages. The this is a gamma ray in the first track, and then the depth track. There is a compensated neutron log. There were tagged proppants that were used to identify the placement of proppant during this hydraulic fracture stimulation. And we have a temperature log from the DS, which shows some effects of shows some results from Warmbek. And then we have the distributed acoustic sensing panel here. So we're trying to stimulate these zones, and there actually is some stimulation that was hopefully done a little bit lower. We don't see that kind of any significant results. And then integrated with this are the production logs showing the velocities of the fluid velocity log and the resulting production profile that was obtained from that. So doing these combined diagnostics and using them, show here that the results, the proppant, the DTS, the DAS, and the production logging results that were all integrated to get information that they use to better calibrate their geomechanical models and also to some extent their reservoir models, and they use then these models to optimize the field development. So they started out with a model that they found did not quite, the modeling results did not quite match what they had seen from their combined diagnostic tests. Use them to recalibrate their models, and then use these updated models to optimize their field development. So this was a very large economical incentive for doing the process, the improvements that they'd seen. One of the interesting aspects of the monitoring was using the DAS to during the stimulation to evaluate the how effectively they were able to frac in each of the perf clusters. And what I'll break, this was a combination of the DAS, the distributed acoustic sensing intensity during the stimulation, and then strain monitoring. Detailed strain monitoring that was done during production using a Rayleigh frequency shift type of distributed strain sensing. Focusing on the DAS intensity during the stimulation, this basically is a depth plot on the horizontal axis. And with each of these circles, the red and the green circles are indications of specific perforation clusters. And we see that as we were pumping, excuse me, that where you have the greens, the yellows, the greens, and all the way to the reds, with the red being the most intense acoustic energy that is picked up. Again, this is a time axis. So we've got depth going in this direction horizontally. We have time going from the top to the bottom, increasing. And we see that as we are pumping, we see this acoustic energy. And each of these zones that have a lot of energy are the relative amount of energy is going to be related to the amount of proppant of fluid and proppant that is pumped into each of the perforation clusters. We see that we have some zones, some clusters, for example, this one, where there was no acoustic activity. Excuse me. So after some production, time on production, the distributed strain sensing measurement was made. And what we are showing down on this axis, so this was after several months of production. We have, this is the zero line. On the vertical axis here is the strain change from the initial installation time to the time, the present time of this measurement. So this is actually showing the strain change. This is the zero line. This dotted line right here is zero strain. We have a positive strain and it going up and a negative strain going down. The absolute numbers that you see there are not quite as important as, although these are listed from, for example, from here from 0 to 60 microstrains. And the way that these are interpreted is that when you see a significant strain change, that is indication that the rock around the, the strain change occurred from during production when you were having a drawdown to the time when you have a shut-in of production. So basically allowing the near wellbore region to repressurize. And you can see that there are significant strain changes at each locations that are noted in green here. We got this, very nice prominent strain peak in every single one of these. The ones that are red have absolutely, no strain change at all from production to shut in. And then overlaying again the original DAS from stimulation. We've extremely good agreement between what we thought was stimulated and an indication that there actually has been significant production and pressure drawdown at that particular perf cluster. And likewise, for each of these ones that were stimulated, we see that we claimed that we had stimulated are now indeed showing results of production and the near wellbore drawdown when the production is occurring. So again, being able to integrate the results, substantiating a production after a production time period with the what you thought you had stimulated, and having extremely good agreement. And again, this worked into the validation of the updated models that they were able to use. This is an example from a well in the Caspian Sea, and one in which that it was very difficult and very costly to do production logging because it required an intervention. It was a high H2S environment. And this involved actually a pump down of a fiber across a sand screen for a gravel packed well. We have the depth on the vertical scale, and we have a temperature scale on the horizontal axis. We have this brown curve, which is the gamma ray curve, and in color we see the 3 reservoir units that are from which production is. So across this entire interval, we have a gravel pack. And we also will make note of this green line, which is the geothermal. So this was the original temperature, the original geothermal temperature. And we're going to add to this plot the two temperature traces. The first is this black line, which shows what the DTS acquired temperature is in January of the year that this was done, when the well was producing 30,000 barrels of oil per day. Now, 3 months later, they had a drop in total oil production from 30,000 to 15,000 barrels a day, and the production of gas at the surface. So they had they felt that they had gas breakthrough, or they had pressure depletion in a reservoir, so that they had gas breaking out of the oil. And we have indications here in these cooling events. These are wherever we see these large cooling events, we're able to quantitatively calculate the amount of gas that is being produced in each of these intervals. So very good. This allowed them to the operator to eliminate running production logs. They had and also the good results that they'd seen here. They had instrumented, I think, in their first phase of the field development, 10 or 12 wells that had fiber in them for DTS, and ultimately for distributed acoustic sensing. This is an example of using the noise from a distributed acoustic sensing to actually use it as a continuous flow meter, if you will. The horizontal axis on this is depth. So from this is 1,400. This distance is 1,400 meters to 2,600 meters. This was for a gas injection well. And basically the noise from the distributed acoustic sensing, and this is initially displayed as what's called a waterfall plot. So this upper left panel has depth on the vertical axis and then time on the horizontal axis. Where you have dark blue, that's very quiet or very low acoustic energy. Where you have res, that is the highest intensity. And we see from this display, they will take information and apply an analytical technique that basically will give them a downwards noise and an upwards traveling noise, from which they can get things like the fluid velocity. So those are then plotted here, and upward flowing noise, downward flowing noise, and the average between the two of them basically, this is basically a Doppler shift phenomena, and midway in between them gives them the actual flow rate that they're measuring. So, and since it was single phase, what they actually applied is the flow velocity from which they're able to get the flow rate, and then use this basically as a production log, injection log. So doing applying analytical techniques to the distributed acoustic sensing, in this case for an unconventional that's co-producing liquids, we see the highest intensity of the flow is shown in the lowest in the, and we see at the heel of the well, we see basically the effects of fluid buildup and then slugging through that, and then those slugs being carried up to the surface. So if you watch the noise, these of So this waterfall display that is here with a synchronized in depth with the schematic of the complete or of the well. So we've got depth and then time, and what we are doing here is we are rolling this display. We're scrolling through time, and we're watching the synchronized play of the flow, again with the highest intensity of flow, highest noise from the flow shown. These are basically like an ability to watch where specific flow events and use that to diagnose your production along the horizontal well. There's another example this is from the San Joaquin Valley in Kern County, where they have a large number of wells, a very low permeability rock, but they are doing a water flood. And they decided to use distributed temperature sensing to measure their water injection. They were injecting into 2 zones. So we have a schematic of the well here. They have, it's a dual completion, so injection into the top zone and into the bottom zone. And what they do is the formation that is above the injection formation is undergoing a steam flood, a thermal flood. So they will shut in injection for a short period of time. The water in the injection tubing heats up. Then when they restart their pumps, they've got this hot water slug that flows down, and they basically time the position of that slug as it goes down through the well, and they use that to calculate the velocity of the fluid. So they use it. It basically becomes a DTS, a distributed temperature sensing type of equivalency to to a spinner log. So they get an injection profile. After the first pilots, they found that they had advantages over radioactive tracer fluid injection logs, much more accurate measurement of their injection profile, and they found that they were able to eliminate running spinner logs with this, which was which was actually one of their desired actions, because their wells very often would start to see some geomechanically driven damage, so they could not get logging tools down in the well. And what they were able to do, and this is a very low cost, very marginal operating environment, that starting in 2009, they made a commitment to instrument a large number of wells, basically 1 well in each injection pattern. And they instrumented over 100 wells with the optical fiber, with their target that ultimately they would continue adding into their drilling program to instrument 60 of these wells in the field per year. It was not a casing deployed for fiber optic. They were able to take advantage of their drilling a large number of wells, so they basically could do this as a fiber optic deployment factory, if you will, and came up with a low-cost and very reliable system. Something that added, I think the added costs in their wells was something $60,000 or less per well. So a very good result. This is explained in detail by Mahmoud Rahman at that time with ERA in California. For injection monitoring during when you are watching for an out-of-zone injection, we have an example from an onshore water disposal well. We had DTS behind casing. We see the the shale log is basically plotted here. And the notion is that they want to do a lot of injection, but they want to make sure the injection is contained in this one reservoir unit so that they do not fracture up and they do not get any flow into any of the shallow aquifers, the potable aquifers. Let's see, I know that I'm getting short on time. I'll go through this, but what they were able to do was to show that after about a year's time, that they were able to contain the injection even as they started a fracture, but they were able to show that the fracture only grew up to this capping shale here, and it satisfied, the DTS satisfied the government regulations of having to pull the completion and do temperature logs to look for out of zone injection, to do that every year. We have an example from using a fiber optics, and I'll go through just very, very quickly because of time, because that shows an example for an acidization of a carbonate reservoir using an instrumented coil tubing, in which they ended up doing this in the Val d'Agri field in Italy. This was an optimized process where it basically was comparing the initial DTS derived production profile with one that occurred after they did the acidization. They would then use this analysis on the fly to optimize their diverter as they needed it, to make sure that they stimulated all of the reservoir units. The use of distributed acoustic sensing for basically 4D VSPs. You can make a 3D VSP measurement. This is from a deep water reservoir in the Gulf of Mexico. The work that was done at Shell, I believe, at the Ursa platform in the Ursa field. And we see the VSP from 2012. They did another one in 2015. So this is actually showing the results of the difference. This based on the difference between the 2012 2015, and they identify there's like water, the water displacing oil and gas coming out of solution, and so on. So extremely valuable information. Likewise, time-lapse VSPs in the unconventional stimulation of unconventional wells, being able to see where you have fractured rock. And I'm going to move right here to the combination of the acquisition of microseismic via a fiber optic cable in a monitor well. So we have a vertical monitor well, and we have two wells that are horizontal, shown here, well A and well B. Well A is going to be stimulated, and we're going to monitor two things with the fiber optics. One is monitoring the microseismic events and using those to help map the position of the fractures. The other is looking at the strain of the well, the vertical strain, and converting and basically watching the rock deformation as the fracture moves towards the injection well. So we have the strain measurements that are done here. This is a time axis going from left to right, and this is the vertical depth section here. And we can see basically as injection has started at this time, and we're starting to pump fluid and proppant as the fracture has been created. These black dots that are shown here are basically the microseismic events, and we can see the overlap of those with a very good match with the growth of the fracture that we're seeing from the strain monitoring as we proceed in time. So extremely valuable in understanding fracture growth, being able to fit back to fracture models and use those for the optimization of the frac pumping, as well as the placement of the perf clusters. Just very briefly, and we just mentioned that an example of a well integrity issue, in this case, a completion integrity. This was using an optical fiber that had been pumped and actually was one of the wells from the Caspian Sea field that I showed, where they started to produce sand at the surface. And what they show here is the DAS, the total energy plot, and they were able to pinpoint the point of sand entry. They were hoping that it was occurring lower in the gravel pack, so they could just set a plug, but they had to live with it since it was at the top. But they at least knew what the conditions were. They were able to produce by backing off on the production, by choking back the production. This was based on an OTC, an Offshore Technology Conference paper from 2010. And this, by the way, is the first publication showing an in-well application of DAS technology.
So
Likewise
Dennis,
on the sand.
I
Yes.
think we're going to have to wrap up. We're at the top of
Okay.
the hour.
Okay.
I want to thank everyone for submitting their questions today. We will make sure that Dennis has a chance to respond to you via email. And later today, you'll receive a link to a recording of today's webinar, an evaluation form, and a link to register for in-well fiber optic sensing scheduled for November 4th and 5th in Houston, Texas. And it looks like Dennis has ended on a summary of his presentation. So we'd like to thank everybody for participating. Goodbye.
Thank you.